let me know about the time. Yeah, hello. So today I will continue talking about this Kontsevich formality theorem that I talked about last time. And so let me just recall you what this theorem says, at least for the people who can see what's written on this part of the board, is that you take a manifold and there is an L-infinity quasi-isomorphism between the multi-vector fields on the manifold and the multi-differential operators on this manifold. And what we saw last time is that these multi-vector fields admit this brackets, the Schouten-Nijenhuis bracket, which is an extension of the normal Lie bracket, and I mean, it's, when I say quasi-isomorphism, it's something that induces an isomorphism in homology. Here we see this with zero differential, and this also comes with a wedge product of vector fields, that we see this as a product. Now, on dipole, you also have some Lie brackets. So dipole is a subset of the homomorphisms of a tensor power of the C infinity functions to the C infinity functions. And in general, when you have something like this, you can define the Lie bracket, which is called some sort of braces Lie bracket, where you take some morphism F and you plug G. So this notation means you plug G in every possible places in F. Now, the multiplication mu is a more Cartan element of this Lie algebra, so you can define a differential just like this. And the whole point of this is that this admits a product, and this also has some kind of product. So making this Gersten-Haber algebra, we'll get there. But this doesn't, because this product doesn't satisfy the properties that we want. And so after all this introduction to Hochschild cohomology and things that I did last time, I started working with this notion of operad, and today I will be talking about operad. So let's just recall more or less what were the definitions. So you would so recall. So let P be an S module. So what was an S module? P is just something that decomposes in a series of vector spaces for all n's, including 0. And each one of these spaces has an action, a right action from Sn. So this Pn is supposed to somehow represent the operations of with n inputs. And we had defined on these sort of structures, we have some circle product, making this a monoidal category with where this more or less, let me just be a bit vague here, represents you taking an operation with k inputs and then plugging in k things in your inputs, where these k things are again some sort of operations. So k. And I think this is all we need to define what. Oh no, this makes this space of S modules a monoidal category, and the unit of this monoidal category is this I, which is given by your ground field if if you take, so IN.
This K is an integer that gives you the right, which is that Pn there, so it's one
Yes.
of the vector spaces.
Yeah, so
the PA1 is also another
is a new number. So the idea is you have some element here of pk, and by having an element here of pk means that this element has sort of k inputs, and in which one of these inputs you'll plug in a new operation. This sort of represents a composition of operations. So here you just put an operation, and when I say an operation, it's some operation with A1 inputs, some operation here with,
so A1, AK are the,
yes, and then this whole guy here will live in P of the total sum of. So we'll be leaving this composition. So how many inputs you have? You have A1 plus AK, right?
it's not yet there. You have to
No, it's in P circ P of that. It's not, and okay, we'll get there in a second. And so you just have the identity of this thing, which is the ground field, if n is 1 and 0 otherwise. Good.
P is an S module, but P circ P is another S module.
Yeah, P circ P is another S module. Exactly.
So the tensor here is kind of
Yeah, there are these this tensor is over K of Sn, which, so this Sn structure action is this thing that encodes the permutation of variables. Yes? Sn, sorry, Sk. Yes, n doesn't really exist in this equation, does it? Yes, and here here this has a right action by Sk. This has a left action by Sk by permuting these guys from one to the other. Good. So you say that P gamma mu is an opera if you have, so the point is, when you write something like this, you want to represent composition of operations. So you want a map, you want this to be an operation itself. So that's where this multiplication map intervenes. So it's the same thing when you have, say, a group and you want to define what a group multiplication is. You give a map from G to G. You can immediately write here, if you want, GH living here, and even ignore the comma if you want. But when you write GH, you're implicitly thinking about this map that will give you really the product in the group GH. Here it's the same thing. So I should usually denote this. So since this is some tensor product of spaces, I should denote this by mu tensor, say alpha 1 tensor alpha k being sent to something else, where this is the sort of the special guy, the one that receives the inputs, and these correspond to the inputs. But when I have a structure of an opera, instead of denoting things like this, some people denote it like this, but I use this this multiplication map to implicitly actually denote things like sort of mu alpha 1 alpha k. So I use some sort of function notation, because an opera in any case is supposed to be describing composition of things. And then you have this compatibility.
And it's really what it is in the case of the endomorphism opera.
Yes, it is. We'll get there. And there are then the natural axioms. Oh, sorry. And this would be some map from I to P, and you have all the axioms you can imagine. So if you have three guys like this, it's associative, and when you compose things with the unit, and this is supposed to represent the identity. So whenever you have some operation, you can plug in identities, and this is not supposed to change anything. So usually people identify this K as sort of space generated by some identity of in Q. This is not supposed to be seen as a map, but it should act as a one, or sorry, Q is P. Even though, yeah. Okay, so this was what an operad was, and it still is. And the other definition that I had was an algebra over an operad, right? So let A be a vector space. A is an algebra over P if we have, so if we know how to compose, how to apply operations to elements of A. So if we have a map, it's some sort of multiplication map also, but now instead of from here to A itself, where, I mean, here you can, it's defined like this. You see A as something in arity 0. Yes, these are what we call operations in arity n. I think I didn't say this today. So it's just the data of a map from here to there, then that is compatible in all possible ways with the unit and the composition. So for instance, just to write one of these axioms, if you have this, there are two different ways you can get to A. Either you apply the composition map here and you do nothing on A. So, and in that case, you obtain here P circ A, and then you use the multiplication map, or you can go to you can first do the second two and apply. So you do the identity on P, circ multiplication map, then again multiplication map. So when I write this notation, it's so if you have maps of S modules, since these are tensor products, this is essentially the tensor product of maps, but you would see what I mean. Do you? Don't? Maybe if you don't, I can clarify. And this is what an algebra over an operad is. As an example, if you have, say, a Lie algebra, I mean, this tells you, so the Lie bracket is something living in P2. It gets two inputs. This tells you if I take Lie bracket of A1, A2, so of course these are all tensors and stuff. This is what you usually write as A1, A2, and this should be an element of your Lie algebra, and this map is tells you exactly what kind of element this is. Good, and I think this is what I said last time that will be needed still today.
I want to conclude here. So
Yes.
You don't really compose your bracket with element A. So A is something like the infinite direct sum of all tensor powers of A, is it?
I'm sorry?
Is A something like the infinite direct sum of all tensor powers of A?
A is A. Yeah, when you see A, but inside of this, inside of P circ A, so P circ A is some PK tensoring many many A's. So actually, since here there only A is identified with A0. So actually, you're tensoring K times A. This is just yeah. In this case, you have a Lie bracket. Yes. So let me continue with introductory notions of operands. Now, just some examples of then some operands. You have, I mean, what are the main examples? So for every algebra, you can think of really a pure algebra, nothing with co-multiplications like in co-algebras. There is an operand representing it. So there is an associative operand, the Lie operand, the commutative operand, the more operands. We'll get to the Gerstenhaber because in the Gerstenhaber we have to be a little bit careful because there is this product with so the Lie bracket has degree -1 and this is non-graded for now, so we'll get there a bit later. But so if we want to describe just as S modules what's the associative operand in arity N, this is some space that can be identified with K of Sn, right? Because you have the operations that are the multiplications, and you can choose the order of your inputs. Each one of this gives you a new element, so you have n factorial elements, which is this. This is the dimension n factorial, and the natural action of Sn is permuting the variables, which is what you get from here. Yes, which is this? Then if you take the commutative operand in arity N, I mean, the only thing you can do is multiplying things. And since everything is commutative, the order doesn't matter. So it's a one-dimensional vector space in every arity. And I mean, there is just the issue when the case n equals 0 or not. And this will it will be 0 or one-dimensional in the case n equals 0 if you're considering unital or non-unital algebras. But this is not really very important. Anyway, to describe, yes.
The unit you do it as an operation. The unit of an algebra, and that's why you need a 0 arity.
Yes. So if I have, say you have the multiplication, which is the multiplication of an associative algebra. Say it's something that lives in associative in arity 2, right? There is one very nice element that you can plug in here, which if your algebra is unital, which is so say you have, if your algebra is unital, there is this one special element 1 of your algebra that lives in if you're talking about unital algebras, there is some element 1 in S0 that you can plug into any possible operation. And
you read as an operation, it's not an element of A.
Yes. And it should satisfies the property that if you put it here and something else and some other operation here, say alpha, you don't really get anything new. You just get you just get alpha. But okay, I mean, I think this is a detail. It doesn't matter very much anyway. Sorry? If you look at, sorry, at where it is, I'm confused. Can you repeat your question? When I write it like this, I'm.
Means A equals 2, and the element in PA1 is A1 is 0. So the element of PA1 is seen as an operation which takes nobody and spit out an element.
Yeah. So when I write this, this is supposed to be living in P2 tensor. I mean, here let's call PS tensor P0 tensor P whatever alpha is. Yes, something like this. And this will be an operation in P of degree of alpha, of arity of alpha. But I don't know if that's clear already or not. The only point is when you write this, the only idea of writing this is that in the first guy you will input k things, one for each slot, as depicted here in this tree.
And here in this drawing, you would put the guy in PA1 would be just a tree without roots.
Yes. So yeah, in a tree way, this would be, you put here multiplication, you put here one that has absolutely no outcoming vertices, edges, and here you would put some operation alpha, which has some amount of outer edges, and I'm just saying that this is equal or is sent under the multiplication map to just alpha. This might be made a bit, yes.
So this arity 0 can be seen as just not.
Yes, yes. So you weren't here when I mentioned that, but you identify like an algebra with an S module in arity 0. And I mean, that's what you want here to make sense. Here, you're supposed to have an operation that gets k inputs, and here the inputs, I think this object is somehow a bit more intuitive than considering this, because here you're composing operations, which is something that most people are not very used to doing, especially because in most algebras in most normal algebras, you only have one operation or at most two. So you have a Lie algebra, you only have Lie brackets. So the operations are compositions of Lie brackets. Whereas here, I mean, you really see you have some piece of structure, maybe a Lie bracket or a triple, or this operation, and this map is telling you. So here you have 3 A's, and it's telling you if you put the 3 A's here, I mean, you're supposed to obtain something inside the algebra, and it tells you what's this element. Yeah, so it should be gamma A of this A, B, C is some other element, and the whole point is that usually this is what we denote by this. Yes, and what I was also saying the other day is that then you have the relation like the Jacobi identity will come from this identity, this map here that will send, say, this sum of the three of these compositions of Lie brackets to something. So the Jacobi identity is encoded in this map in the case of P equals Lie. In any case, trying to actually describe the opera like this is usually something very complicated. So we saw last time that there is you can both see an S module in sort of two fashions. Either you see it as an S module, or you see it as a functor that sends some vector space. So if you want to see P as a functor from vect to vect, would be the functor that sends V to, I was even calling this probably V tilde or P tilde or P bar or something. I mean, you have a functor that does this stupid thing. And actually, with all the definitions we have, you can even see that tilde is is monoidal in the sense that it commutes with taking circles. Well, I guess I'm just adding complication that is completely unnecessary. But the idea is that maybe sometimes it's easier to describe an opera just by describing how it acts on vector spaces using this identification with functors. So, for instance, if you take the associative opera on some vector space V, for instance, you get the tensor algebra of V. And like this, for instance, it's easier to describe what's the Lie opera. So the Lie opera on some vector space V would be the sort of the subset of T V. I don't know, made out of, how do you call this? The Lie words in TV. So whatever, it's the thing generated, the things generated by A tensor B minus B tensor A, right? Yes.
So these are the three P algebras, this guy.
Yes. I think that's not very important for today. Any case, no one really cares much about these descriptions, I think, because in practice you also describe operas by relations, no? Yes?
So far I think you only talked about basis elements, right?
Basis?
Yeah, you always took K basis and described stuff on this. So I guess you assume that everything is K linear and so on, right?
Yes. Everything is K linear. So no operas can describe groups, for instance. So everything is by default, at least, I mean, I think there is not a single object that I talk about that is not a vector space.
So as before we also said what is the difference to universal algebra. So groups you can get by universal algebra, but
yes. Yes. Now also just an important notion we need is the notion of operatic morphism. So operats form a category. We will define what the morphism is. Morphism gamma from P to Q. So let's say P and Q are operats. Let P and Q be operats. A morphism gamma of, no, it's a terrible letter. A morphism F of S modules is said to be a morphism of operats. Is a morphism of operats if it commutes with composition. So if all the reasonable diagrams you can write commutes. So if you have F, you can define F circ F, and you'll send P circ P to Q circ Q. But here you have multiplication map in P to P, and here you have F to Q, and here you have the multiplication map in Q, and you want this to commute. And also the same thing. You also, so the opera always has this identity. You also want it to commute with the action of the identity. Essentially, it's just telling you in a more informal version. So this tells you that if I take mu of so let mu A1. So sorry. In PK and A1.
We don't call them use, but with some indices with the hierarchies.
Because this the first guy is somehow some distinguished element. I don't like calling it the same thing. And alpha I also in P of sumarity. This tells you that if you make the following composition, so in my notation that I described here, if you plug alpha 1 until alpha k here, so this is something that is living in P circ P that we by this map we also see this living in P by the multiplication map. What it tells you is that if you apply f to all of this, it's the thing that you would expect. It's the same as applying f to each one of the components. So f of alpha 1, f of alpha, okay. And also the other thing, I will not write the commutativity with the diagram, but it tells you also that if you take the unit, the identity in Q, so that in P, the thing that does nothing will be sent to the identity in Q. Now, what's very nice about these morphisms of operands, you have, for instance, so example.
We have something like inclusion morphisms from to associative.
So you have the other way around. So example, you have a morphism from associative to commutative, because whenever you have, because I mean, what's canonical? It's canonical by if I give you any multiplication, any multiplication where order matters, it's canonical to make of this some multiplication where the order doesn't matter, whereas the other way around doesn't go. So you have a very nice canonical map from here to there, which is a morphism of operands. And in particular, what does this mean? So let me call this F. I won't describe it explicitly, but actually, if you see it represented like this, it's just projection. Anyway, what does this F, what does this imply? Say you have A. Sorry?
For example, in characteristic 0, you can also come back to your section of this.
Yes. You have a section as vector.
Of the one product, one of the factorial of the other product, another order, and summing them up, or taking them in each component.
And this is a morphism of operands.
But I'm not sure about that. That would be my guess of the candidate for this.
I don't know. Well, let me think about it afterwards. Yes. But everything is of characteristics here. So if you take like an associative algebra, what does this mean under this interpretation? It means that there is a morphism from S circ A to A, right? Sorry, commutative. So you have a commutative algebra. So you have a morphism from commutative circ A to A. But the fact that you have something like this means that you have some morphism like this, which is just F circ the identity of A. So essentially, what's this telling you? It's just telling you that a commutative algebra is also an associative algebra. Brilliant. But also, so you also have say a morphism from lead to S, right? So, and this means that you can make any associative algebra a Lie algebra. Of course, you can compose these two morphisms, and you go from here to here, but this is a bit stupid. If you take a commutative algebra, you say it's associative, and then you see it as a Lie algebra, it comes with a zero Lie bracket. So I guess this map is just the zero map.
No, I mean, the usual product is preserved. I mean, only the Lie bracket part is mapped to zero.
Yeah.
So it's not zero on the whole SN module, but only on that part of the SN module which represents the Lie bracket, not on the product.
But that's only
Yeah, they're only Lie words here, sort of.
Okay.
See?
Okay.
I mean, when I say zero, it's not completely zero. So it's zero in every arity except in arity 1, because here identity is, I mean, not doing anything. The composition of not doing anything is not doing anything, right? Yeah. But so these operatic morphisms are nice. In particular, I'm very interested in some specific operator, because as I was saying, the problem here is that we don't have directly a Gerstenhaber structure. And I want to put some sort of homotopy Gerstenhaber structure there.
I guess this is a nice remark to make. Doing nothing is not the same thing than smashing everything into zero.
Yes, it is. Yes, it isn't. Anyway, this there is a relation between a Gerstenhaber algebra and a Lie algebra, and this is given by the fact that we have morphism from Ger to from Lie to Ger. I haven't talked much about Ger, because for Ger we just need to talk about the differential setting. But in any case, we're more or less now aiming to go to get to this, and then trying to get from this to make some sense out of this. We'll get there. Should I talk about the endomorphism operator? What time is it? 42. I should be over in 1 hour. Okay. Then maybe let's skip this. I don't know. I always take more time than I expect. I would say that I can do this in 1 hour, but if I finish early, it's fine as well. Now, so new subject for a while. Take M some S module. So it's something that has something in every arity, but I mean, no operatic structure. We don't know how to compose things. If we don't know how to compose things, I mean, how do I explain this better? Say you have a vector space, and you want to make an algebra out of this. But the vector space a priori is not an algebra. What you do is, the only reasonable thing to do is then you say, okay, I multiply this. Either you say it's zero, and this is very canonical, but if you want to do something non-trivial, you can say, well, their product is their product, and that's it. And by this construction, by doing this, you're creating the tensor algebra over some vector space. This is a free object, so this is a free algebra on a vector space. It's a tensor algebra. Fine. Now here we want to also construct a free operad out of an S module, and I mean, you can define it rigorously. I think this is a waste of time for this, and you can just say what the idea is. So what can you do without imposing zero relations on your things? You take some guy M in, say, in M, say in M4. So it's some guy with 4 legs, and And I want to put here some M1, some M2, M3, M4. And I want to say what this composition is out of just this data. So first of all, this should be something that should be living in it should be living in something on arity, the sum of these arities, so the sum of the number of legs that each of these guys have. So M1 plus M4. And what is it? I'm just saying, I say, oh, well, it's something that I build. So, and this something that I'm building, if I impose absolutely no relation, it's the free operad over this S module M.
So basically, it's a new S module which coincides with mu circle mu. Basically, that's it.
I'm sorry?
So how do you call your SN module? Mu? No, the S, big M?
This is M, sorry.
Yeah, so as the free M as the SN module is M circle M.
More or less. So it's more or less because, okay, so far, yes, this is actually yes, it's living in M circ M, this guy here.
It's exactly M circ M.
So I mean, in this particular case, it's even contained in so M4 tensor some M's, right? 4 times. But yeah, the point is then, okay, but if you take a vector space and you only allow to multiply, you can multiply 2 guys in the vector space, you will obtain what you usually call you obtain T2 of V, which is the set of A tensor B for A and B in V. But then the problem is you want to make all of this an operad, and you can already multiply sort of guys which are just living in M. You can multiply and you end up here. But then you want to to compose things here with some other things. So you need more compositions. And what do you mean by composition? By imposing no relations. This is just depicting a tree and.
So can you just write down what this free M thing in this module is? I think it's just a direct sum over all K, such that M to the circ K.
Not a direct sum is a cool limit, right? So, right? Okay, yes. So you can define it inductively. So let's just write F for short. So you define inductively F1. So by being your original M. So these are the sort of the ground operations. Then F2 should be M composed with M. But we have to. Should I include this too? Yes, plus M. And there is some inclusion here. Yes. Okay. Morally, I think it should be what you're saying. Maybe there are some details to be taken into account.
Can you write down F3 for just getting an idea how the process continues?
So
I guess it should be M circ F2 plus F2 or something.
But yeah, so what you have then, if you continue, you can you have something like this where you make more compositions now, right? And I think it's not really very important to describe it like this, but
is the induction process something like this? Fn plus 1 is Fn circ M plus M circ Fm.
So yeah, so I guess F3 should just be
M circ
F2 circ M. So you can plug in abstractly every guys in M that you want to put, and then you also sum M, something like this.
Probably just F2 because M is already included in F2.
So wait, is it?
Yeah. So I guess there should be also some M sort F2, and there should be also a copy of F2.
Yes. So there is something here. In any case, the point is, it's not very complicated to understand what's the free operand over an S module. It's just you abstractly compose. You don't impose absolutely any relations. And a nice way to describe this is with a tree. And yes.
Isn't this the same thing you were having before when you considered this P circle B?
Yes, and this comes from the fact that that this is exactly.
But in P sub P, you have just 2 layers. Here you say that you want to have arbitrary number of layers. That's the difference.
He had only 3 of F2, and now
Then
he has 3
there is
of
some
arbitrary
relation.
Yeah.
Where?
I mean, well, this is third.
There's no cert.
I mean, sorry, I understood that the operations were encoded in the projection, in the composition.
In the composition map, yes.
Before giving the gamma, you're just taking whatever.
Yes.
Exactly, but here he's saying the thing that you will want to compose are the trees with the alignments of composable corolla.
No, this will be an assignment of a particular gamma.
No, that will be the P. That will be the P.
But you're having a problem with the rigor or with the intuition. That's what I don't understand.
No. Okay. Look once again. Let's assume that the new key for you is the set of trees of composable things. If you take 2 trees like that, you can compose them, and it's a new tree of the same form. Okay. That would be your gamma. Okay.
And yes, so imagine this is like a space of trees, and composition is really plugging trees one into the other. So just really, so if you have gamma of this, but say, I mean, these trees are labeled with some elements. So if this is M, I mean, then composition is just you start with M, and then you put here this M1, and maybe it's a bigger tree, and it's just composing. Then you also have an identity on operads, and here the identity should be just I don't know, a tree with a stupid tree. Identity is abstractly like an empty tree. Yes. And why do I care about free operads?
Oh, sorry.
Yes.
You take the free operand on an F module, you have just one operation, and F2, you get the operand concerning non-associative.
If I take the free operand on what?
Yeah, there's one operation in F2.
So M is just one-dimensional.
Okay, yeah.
In arity 2. You will get the associative operand. No?
We get magma.
I mean, no,
Because yes, we don't associate. Yes. So what are you saying?
I mean, that's what the question.
Your question is, what is this? It is yeah. So it's not the associative operand. It's something bigger, because in the associative operand you have, yeah, it's a magma if you know what a magma is, but so in the associative operand you sort of have this relation, right? You have this. Here you don't even have this. So these two guys are distinct elements. So say free of M in arity 1 is just the identity. In arity 2 is this. In arity 3 you have, I mean, you have 2 possibilities plus every way to label these guys here, right?
Yep.
So yeah, well, it's computable, the dimension. Don't feel like doing it. Yes, why was I explaining things about free operads? Because then a nice way to describe operads also is by generators and relations. As sometimes it's very nice to describe a group with generators and relations, right? For operas, it turns out that this also works. So you can imagine what an ideal here would mean, right? It's something that is closed under composition by anything else. But in my particular case, what I want is, you can imagine, I give you a free opera, and I said for instance, this free opera that Konstantin asked me to describe more or less. A priori, these two guys are different, but then I can take some R, some set of relations that in this case should be something spanned by this minus this. And when I say spanned, I don't really mean spanned. I mean somehow generated. It should be the ideal generated by this element. And the point is, when you take this,
You mean all the trees that you can plug on the top of these two trees? And then
yeah. And if I take free then of this M, and I quotient by whatever is generated by this relation, what we get is exactly the associativity condition, and so this should be this associative opera, right? So the only thing I'm a bit hand waving is how to define an operatic ideal, but you can define it as being exactly what you need for this quotient to make sense, right? That's how in.
yes.
Yes. Yeah. So an ideal is just something that if you circ either like this or the other way around, and you use the multiplication map, both of them actually land in I, and I really shouldn't be calling this I, because I is what I was calling the unit. So
you cannot get COM with this approach, right? Because the commutativity, the additional commutativity relation is somehow encoded not in the S.
yes, you should have started to obtain COM, I guess. You should have started with M with the. What am I saying? Yes, you should be able to.
And you should be able to get
Yes, I mean, because every opera there's some quotient of a free opera, right? You just have, but yes, for the commutativity you have to impose the correct conditions on the.
Okay, so it's
Right.
It's the same diagram, but
Right. The point is, I'm just quotienting here by trees, but the point is, you can, for instance, say that quotient by the following thing. You can quotient by 1, 2 minus 2, 1. So yes, you can obtain COM. You can obtain whatever you want.
But then you should for this R prime, and then you need R and R prime together. And you need to.
Yes. This would be just to obtain the commutativity. Sorry?
Because I think you should take another M, because M is a small.
Yes.
You just take
Here you have.
S module, which is one-dimensional, and
No. You mean S module, one-dimensional linearity 2? You mean?
yes.
And with what? You say
With
change
S2
the.
acting trivial.
Yeah, but this is already what S2 is doing here. I mean, there's not so many actions you can put on K from S2, right?
Yes.
But shouldn't M2 be in this
Yes.
case two-dimensional or something?
For the free map.
Because because you can switch, so the M2 should be two-dimensional, not one-dimensional.
Yes, in a social.
So it's
So it.
Yeah.
Yes. Yes, maybe we can move on, because I mean, this was clearly something that I wasn't thinking about, and this all started with Konstantin. It's your fault. So ask Konstantin at the end of the talk if you want. He knows. Or I can try to think a bit about this as well. Now, what do I want to talk about? Causality. We'll get there. Now, there are most of the nice operas that you know, even before knowing what an opera was, are what people usually call quadratic operas. So, well, let's say definition. An opera is quadratic. An opera P is quadratic if P can be written. This is a B. Written as so P equals 3m over R. So all operas can be written like this. So far, this is a stupid definition, but now you impose all the relations to be quadratic relations. So R should be living in what I usually call sort of 3/2 of m, which would be that in the case of the tensor algebra. And here it's trees with 2 levels. You know what I mean?
F2 mod F1.
Great. Exactly. So no. Okay. Very nice. So it's M circ M. So idea, these are 2-level trees. So 1 level, 2 levels.
Are you sure?
No.
Because I thought they also include 1-level trees, right? For example, commutativity, or is comma should be comma?
No, this is what people call quadratic linear. And this is not necessary for commutativity. It is necessarily, say, for BV. BV algebras, if you know what they are. BVR is quadratic linear.
Yeah, but for
Yeah, if you don't know, it's false.
I think the operator which encodes mechanisms, it's not quadratic. And because it's rather counting the number of corollas to say that it's quadratic. And here you have more than 2 corollas, you have 4 of them, right?
Okay, you're right. Oh, damn it. Then it's really not this. So, an opera is a tree. So, I'm sorry. Yes, it's not 2-level trees. It's supposed to be trees with 2 vertices. So, which in the examples I was thinking, so 1 vertex, 2 vertices, and yes, this is what the 2-level tree is. Yeah, sorry for the imprecision, but you understand what this means, right? So here I'm not allowed to put in anything or seeing in a way I plug in the identity.
Okay, so why the identity you get called?
Yes. No, still not.
Because in this identity, in this commutativity idea, you only have 1.
Sorry, can we repeat this thing neatly and
Very good. So an opera is an S. Right. So a vector space is a space with the following axioms. You have an opera is quadratic if it can be written in this. So the free part is okay. So it's trees. Abstractly, it can be represented as trees. Modulo some ideal, which should be something that is living in this guy, and this guy represents trees. So trees with 2 vertices.
You mean generator of the idea, not the whole idea.
yes.
Yes, so it's an ideal generated by trees with two vertices. Of course, because if it's an ideal, then it means that you can compose it and you still stay inside the same ideal. But if you compose something with two vertices with something else, you'll get more vertices, right?
So it's not mu super mu, or it's mu prime super mu. There's
No,
this
it's M
prime.
circle.
Okay.
It's inside M circle. There's a subset
Yes.
right after the R.
Yes, in particular, it's inside. But so you can probably see it sort of as M tensor, sort of one M and then many Ks. So you always choose the identity, and you can move the M around and decide where to plug the M. Anyway, a good thing about this is that all the operads you can think of are quadratic. So namely, unless you heard when I said BV was a counterexample. So in particular, like S associative operad is, as I said, it's the operad. It's the operad quotiented by this relation, and this lives in. This is a tree with two generators. So this is this free of this modulo the ideal generated by this. Also, Lie, which was a bit hard to describe before, now it's just also free of this. Yes, so I don't need this, and it's exactly what Marco was saying. So I can avoid this relation because this relation is linear by saying that here the S2 action acts trivially, and here the S2 action acts by the sign representation. So you apply the transposition and you get a minus sign. So it's a different thing. And here you,
But as Gomes said, you need actually two generators and S switches.
The one with the leaf labeled 1, 2.
yes, but I can avoid that by doing what I did, can't I? Sorry.
I think you
M should be S module.
Yes. M's an S module.
If you don't want commutativity, that S module should be at least 2.
But it just says I take something completely.
No, but
shouldn't be a community.
No, but it's not. It takes another set of generators. It's not the same set of generators. It takes a commutative module.
Yes. Well, anyway, this is. Yes, you can generate it with just one generator, but then this is an S module. It comes with an action of S2, and you can do it by saying that S2 acts here by sending it to minus itself. You can also do it with two generators and then putting S2 permuting or associative. But no, I mean the natural thing is to say that there is one generator in. Oh.
Then you need to free S module. You said you have a S module, which means you have an action of S and defined on your things.
Well, I think you can also talk about non-signal operands. Either you have two definitions of operands. You have the one where you take into account.
We're talking about the associative operand.
Yeah, but I'm saying that the associative operand you can describe with one generator, but not in the realm of symmetric operands, but just on planar operands.
Ignoring the symmetry, yes.
Okay, then
Yes.
yes.
Okay. Yeah.
But that M is not S module.
So in any case, what we are really concerned with is with
Here we are talking about symmetrical operators.
yeah, but
And M is S module.
Yeah, so we should have first done the talk without speaking about symmetry, just operas and give only the example of us. And then we would say with that we cannot deal with it.
we can't do many
And then
things
we
because
jump on to the-
5 more weeks.
yes.
No,
No, it's just repeating the same thing, but now putting SNs whatever we can. But okay, anyway, you have these operas that are sort of I mean, they're all quadratic. And so here you quotient by the ideal generated by the Jacobi identity, which is a sum of three trees like this. So you can, it's three trees like this, and you permute the 1, 2, 3, 2, 3, 1, 3, 1, 2. And maybe now would be a nice idea, a nice moment to introduce the Gersten-Haber opera, because I will be talking about Kozul, and that's why I'm doing this. And you also have Ger, which is a bit more complicated. This certainly cannot be described with just one generator in arity2. So you have say mu, which represents the multiplication, and Lie bracket, which represents the Lie bracket. I hope the notation doesn't confuse many people. So you know what a Gersten-Haber algebra is if you were here the last time I spoke. But just to remind, so you have some, you have Lie bracket, product, and the Lie bracket is so the Lie bracket is of degree -1. The product is of degree 0. The Lie bracket is graded anti-commutative, and this is graded commutative. And then you have the relation, the normal relations for the Lie bracket. So the Jacobi identity, associativity here. So this is already sort of a mixture between Lie and Com, but also you have the nice property, which is if you do this, you get this. You put plus or minus. Let me call A, B, and C. Otherwise, it will be just too complicated. A, B, C, A, B, C, and here you get. So the B comes out, and that's why the plus or minus, I don't know exactly what it is. AC. So you have this sort of biderivation property. It also works. I mean, this implies that it's also biderivation on the right? So the Gersten-Haber algebra is the free opera, generated by some multiplication and by some Lie bracket, and quotiented by three sorts of relations. So the relations in Com, the relations of a commutative algebra, the relations of a Lie algebra, and the relation and this sort of, let me call it Leibniz relation. Now, this is not a normal opera, it's a graded opera. The only thing it means, I mean, this should be defined, right? So what's an opera? An opera is an S module with blah, blah, blah. Now, for graded operas, you have, can I erase this? I think I'm not going to say anything very smart, but in any case, it should be said. Because we're going to be talking about Lie infinity, and all of these things are graded operas. So graded opera, you start with you say that M is a graded S module if is graded S mod if each of MNs is graded, and you can continue. And then P is a graded opera.
So the grading has nothing to do with the arity.
Completely unrelated. That's why I was saying that we should really be calling this arity and not grading, because then we have gradings.
There should be some compatibility, right? The grading should give you a grading for each arity, for example.
Yes. So each one of the MNs has a grading.
Yeah,
I'm not under.
the grading has something to do with the area.
Yes, it has, but it's
Compared-
in the
Well,
sense that you
the
can.
grading of the whole thing like restricts component by treats arity component. The grading of the whole S module restricts to in each arity component to a grading of the arity component.
Yes, but that's still not saying much, right? But yes, so P is a graded operad. Operad if
The grading of the whole S module is defined by its two pieces, right? So it's trivial. It's clearly compatible. I mean, you're defining it.
It's unrelated, it's wrong.
Yeah.
Sorry.
Okay. Anyway, can we stop this nonsense? Now you say it's a graded operad if this map not only satisfies whatever normally satisfies, but it should be of degree 0. So what does this mean? I mean, it says something very simple. If you take a Lie bracket that's of degree -1 and you compose it with, say, the Lie bracket itself, you should get something of degree -2. And so you can't do n'importe quoi with this thing.
So basically what you're saying here is that you want that the grading is additive when you plug in stuff.
Yes, that's exactly what I'm saying. So if I here take one operation of degree 7 and I compose it with an operation of degree -2 and an operation of degree 3, I should get something of degree 7 - 2 + 3, which turns out to be 8, right? Yes, but now we're not only interested in graded operads, but in differential graded operads. Because why do you care about grading if you don't care about differentials, right? Differential graded operad, you here now, different color. Here, Mn is a complex. So taking differential does not change your arity, but you still have your grading. And then here you still have this composition map. And then, I mean,
So you don't really want to.
no? What was the amazing? Oh, it was the green one, right? And I mean, here if you take some differential d on P, and here if you take the multiplication map, and the only point is that here what we would say this map is something that needs to be described a bit more carefully. And what's the idea? You shouldn't say this is not d circ d. And I mean, these are the standard derivation properties. So if on one hand, when you take d of a plus b, you want this to be d of a plus d of b. Here, this circ encodes plenty of tensor products, right? So you should be doing Leibniz. So yes, so you should this should be yes. Which on compositions, I mean, what does this tell? If you take some composition mu of say alpha 1, alpha 2, you want the derivative of all this thing to be, so on one hand you should have one, so one term should be this, you should also have mu of d alpha 1, alpha 2, and then the other term. So this is what we get. It's a differential operad. At least the grading part explains what happens with Gare. Sorry. And yes, if you're following cohomological conventions, right? I would say it decreases the degree by 1. But yeah, so when I say that this is a complex. It's implicit.
So if one interesting thing is that it acts also on mu, right?
It acts also on mu. What are you calling mu?
The thing you call mu.
Yes, here, which is not an M here. Yes, it does act on mu.
And so on the tree,
And
everywhere.
sorry.
On the tree thing, you go everywhere.
Yes. Yes. So imagine I want to take the differential of all of this. This means that this must be equal to a sum of all possible ways of putting a d in each one of these terms. Thank you. This is nice remark. And diarity is preserved. So each one of the amends is a complex. Yes. Right. Now we take.
So you see the Gesser-Haber bracket coming out of the BB.
Sorry.
So when you have a BB algebra structure, you have that this BB Laplacian does not really satisfy Leibniz, but it has.
Yeah, I think I don't know how to answer your question, to be honest. Because I mean, this is not supposed to be seen as a differential, right? The BV Laplacian, right? Yeah, it squares to 0, but I mean, it doesn't have Leibniz properties, right?
It's not equal at the you make the difference and you make the division.
Sorry?
You write something similar to that, but it's not equal. You make the difference between the left and the right side of the equation.
Yes. Now, everything is well defined. Now you know what Gersten-Haber is. Now it makes sense to. No, it still doesn't make sense because now we still want to put some sort of structure on the poly that is related to Gersten-Haber, and the problem is that this Hochschild complex does not admit directly a Gersten-Haber structure. Yes.
Sorry, I missed. So in Gersten-Haber, batch and V are of which degree?
Yes. So this guy is in degree 0. This guy is in degree -1.
Okay, and the differential is 0.
And differential is 0. Yes. Yes. This is just a graded operad with no differential. Yes. Yeah. So we want to put some structure on the Hochschild co-complex of something, and that relates to the Gersten-Haber. And what I had told you the last time was that even though the poly doesn't admit a Gersten-Haber structure, its homology does admit a Gersten-Haber structure. So what's the good thing about these graded operads is that if A is a, so let P be a differential graded operad, and let A an algebra over P. So an algebra, say even a differential graded algebra. This is the same definition, but when you have this multiplication map gamma of A, it should also commute with this differential. So what does this mean? This means that there is a map from this to this, and this map should be a map of, in particular, it should commute with the differentials on both sides. So this induces some map in the homology of at the homology level, right? So these are tensor products, a bunch of tensor products, and tensoring is an exact functor. It commutes with homology. So, so this is a home. It turns out that this gives us a map from this to this. So what am I telling you? If A is an algebra, is a P algebra, then the homology of A is a homology of P algebra, which so far it's not being very enlightening because you're not very familiar with I guess many algebras with a differential, but this will be very related to this thing here. So essentially what I want to do is I would like to put in, so my algebra A now is the Hochschild complex.
So, sorry, the H of P is another operand, right? You're saying
H of, yes, okay. Homology of P is another operand. I should have mentioned that. When you have a differential operand, differential graded operand, its homology is an operand. So what we, yes, it's another operand. No differential, still degree. Yes, the differential is 0. So what we want, because what I mean, but these arrows are only going in one way. It's not like I can go back. So what we have is we know that the poly is a Gersten-Haber algebra. And sorry. What we have is that its homology is Gersten-Haber. We wanted ideally to put a Gersten-Haber structure there. That's not going to work out. So what we do is we want to maybe see Gersten-Haber as the homology of some other algebra that we will call Ger infinity, and we actually want to find some Ger infinity such that this holds. So we want to go the other way around. So okay, we can't put a Gersten-Haber structure directly on the poly, but we take something that at least works up to homology. And that's our goal for now. Is to construct this Ger infinity, and this infinity here. If you've already seen Lie infinity and these sorts of things, this is exactly the same infinity. So, say we have a quadratic operand. Let's get back to quadratic operands.
Now you're explaining the infinity.
Yes. What I'm doing is, what's this Ger infinity? We go back to this quadratic operand. Let P be a quadratic operand, so it's some free of M modulo some quadratic relation. There is all this causal theory that I will make a super shortcut and say that we define P causal dual, the causal dual of P is P. Now, do I want shriek or anti-shriek? Let's make it it's a something. This. So you take your S module, and so you want to construct something dual to this. And then you put here some duals, and instead of taking R, you take, because R doesn't live inside of this. Neither does R dual. What it does live is R orthogonal, right? So this is where our orthogonal is the set of X in say this free tool of M, such that X R.
So free tool of M star.
Sorry?
So it's free tool of M star, or
Yes, but then it makes sense to apply some elements of the dual to R. And I take all of this and I take the dual again because I don't like to take the dual only once. And this is what we call the causal dual. Now, this is not an operad because the dual of an operad is not an operad. You can imagine what the dual of an operad is called. It's called a co-operad. I could make another talk on this, but since I want, I mean, a co-operad, an operad, you have some multiplication map. There you have a co-multiplication map going in the other sense. So instead of taking tensors of P and obtaining 1P, you take 1P and you get tensors of P. This is not very important because at least I'm not, okay, I'm concerned about this co-operad structure, but for now, I define so let me define directly. I define P infinity to be the free operad generated by P anti-Schrick bar. Good. What's this bar? This bar, this bar is, so you know that this has an identity, right? Because there was an identity in P, so this still has some sort of this identity there. But this identity is a bit too much. So bar is essentially, so bar of P is defined as being P, you just modulo this identity. Because then when you take free, when you do free of something, you already get a free identity. Well, you already get an identity, so you don't want to have two identities, so we forget about this identity. This is a minor detail. The only point is, and this also comes with some differential that maybe I don't have time to talk much about this, that I certainly don't have time to talk about this. The only point then is that from P, you constructed some free operad, and this operad, moreover, this comes with a projection to P. You can actually do this by hand. You check what this is, and you can see that P infinity projects to.
Differential graded operad.
Ah, yes, it comes with some differential. The grading comes from the free structure, right? Because as I said, the multiplication should have degree 0, so the degree of this tree should be the degree of the sum of the degree of the vertices. This is secret. There is a degree shift. Because, no, I'm not going to say why. Now, theorem. Better yet. So, okay, but so this is how do you define, this is how you define L infinity, which is by definition just Lie, and then you do infinity of it, and you also have Ger or infinity or G infinity, let's just call it G infinity.
Can I ask something before you do this?
Yes.
So I'm missing something. So this P infinity, so you take the free operad over something, so that already has what you call gamma.
Yes, it already has an operad structure.
And it's hidden in, but where, so the operad structure of P, does it get lost, or where is it?
No, it is concealed in this D here that I didn't describe. So this D here uses so uses the co-operad structure on this. And of course, the co-operad structure on this comes from the original operad structure on that. So yes, from what I wrote, you don't see where does the operatic structure intervene, but it intervenes here on this D.
But it's very similar to when you do the bar construction, the multiplication you have for the associative algebra gives you the differential. And it's basically what you're doing.
Yeah.
But for operatic.
So magic. If you take all operads that you might think of, so Lie infinity, Ger infinity, Com infinity, many others you might want. All of these are quasi-isomorphisms. So these are, and they're even better. They're like minimal resolution. So it's really the smallest guy you can find that is free and that whose homology is this. So I mean, saying that these are quasi-isomorphisms means that the homology of this is this, since here there is no differential. But so these are resolutions of these operads, and that's really very, very nice. So you say that an operad is Koszul if you ever heard this expression. An operad is Koszul if it is quadratic and it satisfies that its infinity construction, as constructed here, is a quasi-isomorphism. And it's not a general fact, but it's general enough so that it's true in all nice cases. But
so
no, it's
not true that P infinity to P is a resolution.
No, it's not. So in general, you can always find some free operad that resolves your original operad, but this is a particularly nice resolution because you really take P, and this P anti-Schrick is not something very big. And I can even give you an example of this. So in general, if you take an operad, there is this thing that is called the Barco-Bar construction of P that always comes with a projection to P, and it's a resolution. The problem is that this is really, really big because B of P is already some free guy on P, and omega is again a free guy on P. So this is a bit wild. Whereas here, let's say I take P to be Lie or something. Lie is good. What we have is that Lie, I defined Lie as a with generators and relations over there, and it turns out that here, for instance, in arity2, what we have here in free of so you have a three-dimensional space here, and then you have a two-dimensional space here. So this quotient is actually very small, and it turns out that P anti-Schrick is just only exists in arity2, so you can forget about the bar, and it's generated by, and it's one-dimensional. Am I right? I think I'm right. Huh? Sorry.
It's called
What's COM?
neon.
Yes. Yes, of course. No, it's COCOM. Sure. So this is one-dimensional. It's very nice. So you take free of a one-dimensional guy, and what will you have? You have essentially this bunch of guys that you can make with just one dimension, with just one-dimensional space. And if you know the definition of an L-infinity algebra, you might wonder. So a definition of an L-infinity algebra is something with many multi-brackets, and these multi-brackets come exactly from this. So I would like to give more details about this, but there is really not too much time. But I mean, maybe you'll recognize. I have 5 minutes. Okay, then let's prove the formality theorem in 5 minutes. Yes, but given that there are people that have to teach and all of this, yes? It is a cofibrant replacement, yes. It's the infinity thing is a cofibrant resolution of yes. Your question was just this, right? Yeah, the vibrations on operas are just surjections, right? And yes, you have all the lifting properties and everything, so things are very nice. Although, I mean, yes, when you put a model structure on operas, you don't use these sort of resolutions to, I mean, to define the to do the factorization morphism. But I mean, yes, it is a cofibrant replacement. Now, so. Yeah. Also, the fact that you have this means that if I have, say, a Lie algebra, imagine I had a Lie algebra. This means that I would have some map from Lie circ A to A. But I have this morphism. So any Lie algebra, for instance, is a Lie infinity algebra because I have this composition, right? And same thing for Gare, or for any infinity thing that satisfies. I mean, no, actually, for any infinity thing. So yes, our goal will be, I mean, the hardest part of this theorem is now to put, let me just call G infinity for short, a G infinity structure on dipole. And what Tamarkin does, so you have this morphism. What Tamarkin does is, well, let's not put directly a G infinity structure. Let's see what acts on, what's natural on the Hochschild complex of an algebra. There are these plugging in operations, what I was calling the braces operation. And there is some other sort of operad, which is some braces operad. So I'll just hand wave as much as I can now. There is the braces operad, which is an opera that, okay, let me describe the elements more or less. So let's say the elements are so I pick one tree with one root. Then I have some trees. And I mean, this is the braces. The braces opera is made out of trees. Good. How do we compose things? Now it's completely unrelated to the other trees of the free opera. So the way you compose a tree on this is that you choose one vertex and you plug in to this vertex and you connect the vertices to the tree in all possible ways you can. How does this act on the Hochschild homology of some cohomology of some algebra? Sorry, co-complex. What you do is say this element is element mu. So let's say you have not mu. Mu was a multiplication. Give me a name for this. Huh? T. Great. Thanks. So say I want. How do I determine what's T of F1 Fk? So say I have F1 Fk, which are k functions from here to there. What I do is I put F1 here, F2 here, F3. So these guys are actually labeled until Fk, and this is supposed to be a function. How do I? So this is supposed to receive a lot of inputs, so the number of inputs equal to the sum of all the number of inputs. And what I do is I put, so the first input here, A1, the second here, A2, A73, a lot. And what I do is I connect in all possible ways such that the inputs match the number of inputs, and I sum over all possible ways. And this is the function I obtain. All, no, yeah, they shouldn't intersect.
Could we do an example with a tree with the two nodes and some elements?
We can do it.
Okay.
We can do it later. Yes, but so okay, there is this this opera that acts more or less like this, and the idea is that okay, fine, we have an opera that acting here, and actually you can it even comes with a morphism to G, and the whole idea is that actually we can factor this through there, and the problem is that what the Markin does, it doesn't really construct this opera. It constructs this opera. It constructs some opera at B tilde. And then he shows that this opera at B tilde is actually equivalent to braces. And now this all hand waving is very nice, but this is actually very complicated to show this equivalence. So to show this equivalence, he uses this Etinghoff-Kazdan quantization, and yeah. So as you can see, I said in 5 seconds, probably the hardest part of the paper, or maybe not, but still, this is the complicated part. But yeah. And what? And the rest of the theorem falls by. It's an equivalence. It's the canonical isomorphism.
Larger, let's say, than
Yes. And how does he more or less concludes this proof? So there is this there is some lemma in homological perturbation theory that under certain conditions an algebra over some opera is intrinsically formal. Oh my God, I'm just saying. And saying that it's intrinsically formal somehow means that it's quasi-isomorphic to its homology, and these conditions are satisfied if we see D Pauli as a Gare infinity algebra. It doesn't work if we see D Pauli as a Lie infinity algebra. So at the end, he shows that these conditions are satisfied, and he concludes that there actually exists a G infinity morphism from T Pauli to D Pauli, and I think I don't really have time for more. So sorry for this rushed last part.
So we had plenty of questions, so I think we're done.
Yes, yes.